I don't think there's any other questions coming across, so we'll go ahead and get started with the lecture. We're continuing our work on these thin beams subjected to shear loads. And when we ended up last time, we had actually gone through and figured out how to calculate this thing called the shear center. And so we were, this is the slide where we ended up. You can see this image up here. This is a thin U channel, thin-walled, subjected to a shear load. I gave you the hint that it's a good idea to assume that the shear load, the resultant shear stress, or I should say the resultant of the shear stress, the shear load, is somewhere on your cross-section. Most conveniently, it's actually assumed to be off the cross-section just to make your diagrams a little bit easier sometimes. So that's just a general comment. I'd give you that hint. And then the math will track it back to the correct location. So in the calculation we did that concluded the last lecture, I assumed that this resultant shear load was below this cross-section and that it was to the right. And by doing that calculation, and then ultimately in the end summing the moments and setting them equal to the resultant moment. Of course, in this case, it's important for us to say the resultant about what point. So if I assume the shear center was off the cross section, and then I took the moments about the shear center, and I assumed the load was through the shear center, then the moments, because they're through the shear center, have a total magnitude resultant of 0. And so then the individual force components, that is the sum of the shear flows in the individual segments, then must also sum to 0. And from that we calculated this distance EY, which turned out to be the distance of the shear center from this reference point. Now you might say, well, hey, Dr. G, you already knew where it was, so assuming it there kind of is cheating. Well, I want to prove to you that I didn't have to assume it correctly in order to get this calculation correct. So let's say instead I had made the assumption that it was closer maybe to the centroid. That would be, I'd say, a fairly common and arguably intuitive place to put it, although it's not, it turns out to, of course, not be the shear center, but that's a common, I will say, misconception or mistake that somebody might make. And so if we had assumed that it was close to the shear, to the centroid, in this diagram it would have been above this lower segment rather than below it. And so I can still do the same calculation. That is, I'm going to calculate the moments about the shear center, but now the shear center is assumed to be in this location right here. Keep in mind, of course, that we had these, the forces. I should go ahead and draw these on here for the sake of discussion. F1, F2, and F3. Of course, they were assumed to be in the direction of the S coordinate systems. So I can again calculate the moment about this location. So in this case, what we see is F2 is a distance EY from the moment calculation reference, and then F1 and F3 are both distances of B over 2 from that location. And of course, all three of these contribute to the positive counterclockwise moment. And so the sum of all those three contributions to the moment then must be equal to 0. Lo and behold, if you solve that for EY, what we get is now a minus sign in front of the same magnitude. So the minus sign obviously flips it, and it ends up being back down here anyway. So that's a good and anticipatable outcome. We would hope that to be true. Otherwise, of course, our theories are not sound, but they are sound. So that's a good example of how you can make a poor, I'll say a poor assumption, although it's not a bad assumption. Obviously, it gives you the correct calculation, but perhaps less slick assumption. Okay, I guess the last thing I'll do this example one more time. And what I'm going to do this, I'll draw my forces again. So I had F1 here, F2 here, and F3 here. Let's say I had chosen a point that was an entirely different point. So here I'll highlight that I have put a red letter A on this corner. Let's say I calculate the moments about that corner instead, because of course these moment calculations, they apply irrespective of what moment reference we choose. Equilibrium still has to hold, so I could choose a reference different from choosing the shear center itself. So here I'm going to calculate moments about the corner A. And of course, these must be equivalent now to the resultant shear moment. The difference is the resultant shear moment about this point is no longer 0. When it was a calculation about the shear center, the shear resultant was through the shear center, at least we assumed it to be so for the purposes of our calculation. But now since we're using a different reference A, the shear resultant now actually contributes to the overall moment. So why choose this location is a relevant question. I chose A in this example because now F2, this force, and F3 both go directly through the reference location. So the moment arm on F2 and F3 is 0. F1 is now a distance B from my reference A. So the total resultant moment about this reference point is going to be F1 times B. And that has to be the static equivalent of the shear resultant that's present. So the shear resultant here is Sx, and that is now a distance positive EY from the reference point A. So this is statically equal to this, and then of course we can solve that for EY, plugging in our known value of F1, we get our same magnitude. Okay, so you know, what does that suggest? That suggests that it doesn't really matter what we take as our reference point for this calculation. As long as we are rigorous about our calculation, we will get this right in the end. So just for, I guess I kind of did this a little bit prematurely here. So this one, we assumed it to be below the channel. I've got these images mixed up now. So this one should have been below. This one should have been above. See, this one's assumed above. I drew it below. This one's assumed below, but I drew it above. So there really should have been a negative sign here, except for the fact that if the diagram had been drawn correctly, then it would have been positive. Okay. Anyway, so irrespective of how we choose our point, irrespective of where we place our original assumption, rigorously calculating this will take care of itself with the signs. So I see Nate asked the question in the chat window, will it make calculations easier if you assume roughly the correct spot? I'm going to say usually no, actually. Why do I say that? Well, so let me just draw here for this example. Okay, so roughly the correct spot was down here. Okay, so you don't know where roughly the correct spot is to begin with. Okay, so that's I'd say a general statement. If you're doing the calculation, it means you probably don't know precisely where it is. The calculations are typically easier, so the hint that I would give you is typically you want to assume it off the cross-section. And the reason is because if you put it on the cross-section, like if I were to put it here, or somewhere maybe like up in here, like where the centroid would be, then you often just get too many lines in your diagram that are all close to each other. You know, you get these resultant forces, you get the S's, individual S's, all these arrows, you get this arrow, and it just gets cluttered, is kind of the bottom line. And when it's cluttered, it then becomes easier to make sign mistakes in your calculation. So by assuming it to be off the cross section, it actually then just makes your diagram a little bit cleaner, and you're less likely to make the human error of incorrectly placing a sign somewhere. The other real tip that I'll say is if you have, you know, and we're going to get to these tips here in a minute in a more formal sense, but I'll just give them to you now in an informal sense. So if we have symmetry, one of the things that we know, I've said this in the past, and I'll say it again as we get onto the next slide or two, if we have a line of symmetry in our calculations, or in our cross-section, I should say, we know that the shear center has to be on the line of symmetry. Now, you know, you can place it down here like I did, and of course you're going to assume a resultant, a shear resultant. Now, I drew my assumed shear resultant this way. One might have the tendency to then say, well, why not draw it this way? Okay, and it turns out if you draw it the way that I've drawn it the second time, so this vertical arrow instead of the horizontal arrow, if you're drawing it along the line of symmetry, this resultant force, as your assumed shear resultant, you'll end up being one equation short in your calculations. You know, you need your sum of the forces in the x direction, you need your sum of the forces in the y direction, and you need the sum of the moments. So 3 equations to solve all of these unknowns, what amount to unknowns in the problem. And if you assume this to be along the line of symmetry, you're going to end up being one short. And so instead, what you should do is, if you identify a line of symmetry, like I have here with the dotted line, it's good to assume the shear resultant is off the cross section and the shear load is perpendicular to that line of symmetry. And that's what really makes your calculations easier. Now, you know, the more difficult problems, if you don't have any symmetry, you know, if you've got a cross section that looks like this, then, you know, you can't necessarily make a really good guess about where to place this. And so in that case, you might end up having to actually track both. You know, I might have to choose a point here and then assume both an Sx and an Sy component of the shear vector, and then do the calculations this way in order to really locate the shear center. So that's if you don't have symmetry present. Note, by the way, also that one of the things that you'll explore in the homeworks, these calculations that we've done have assumed, you know, when we made our charts of what we know and what we don't know. So here's one of them. We assumed that in each of these segments, it was at least piecewise constant thicknesses, sometimes constant locations, positions, X or Y values. You know, some of the homework problems, they're set up to make these a little bit more difficult to calculate so that you get a, you know, practice. These ones that we're doing in lecture are pretty easy, and of course don't really apply. You know, easy is not the general rule for aerospace engineering structures. So to give you a little bit practice about slightly more complicated structures, the homework problems typically do things like, okay, we're going to make T not constant, or we're going to make the position X or Y constantly varying, you know, stuff like that, to make these calculations a little bit more difficult. Not because I'm doing it just to be hard, but because real cross sections in real world structures are rarely as simple as the homework problems that, or I should say the lecture examples I've given you so far. Okay, any further questions on that? Okay, so without hearing any more questions, here is my succinct one-slide summary. of steps that you should take to find the shear center when you're given this as a homework problem or an exam problem. So of course, the first thing you're going to do, keep in mind, right, shear center by definition is a function of geometry and not load. The load doesn't matter. It is a property of the cross-section, much like the area moment of inertia, the polar moment of inertia. All of those things are properties of the section. So when you're asked to find the shear center, it would be rare for me to actually tell you a load to use. So what you need to then do is you need to assume a resultant shear load is going to be applied at some location that you're going to assume is the shear center. The tips that I give you: assume symmetry. If there is symmetry, assume the load lies on the line of symmetry and perpendicular to it. And assume a convenient location for your math and your diagram. It's often easiest to assume that the load is outside the geometry just to make the diagrams easier to calculate. And then, of course, with whatever shear load you assumed, you have to compute the shear flows. Those are the Q values. And, if appropriate, the resultant shear forces that go along with your shear loads. And then from that, then you need to apply global equilibrium. You need to sum the moments about a convenient point. And if the point is the shear center, then the moments need to sum to 0, because the moment through the shear center, if you're assuming the load at the shear center, has to be 0. If the point is off the shear center, the moments must sum to be the same moment as the resultant force would impart. Okay. Tyler asks in the chat window, what if there are 2 lines of symmetry? Well, that's a great question, Tyler. One I think you can answer yourself. So let me draw something that has 2 lines of symmetry here. All right, so here's one. Here's another. In fact, here's another, right? For this particular problem, we have infinite lines of symmetry. If there's more than one line of symmetry, then the 2 lines themselves, where they intersect, it is by definition going to be the shear center, because it has to find, the shear center has to lie on a line of symmetry. Therefore, if there's more than one, the intersection obviously is the line of symmetry. So great question, Tyler. Thanks for asking. It brings up a good point. Okay, this is I'm going to make this statement again. Remember, if you're computing about some, when you do these calculations, 2 things that really need to pay attention to. So whatever you're assuming as the shear value, and here I'm going to draw SX because that's what we used. Whatever you're assuming that to be, whatever you then calculate the flows to be, wherever they are, however they're aligned, this is equal to that. So this statically equivalent needs to be that. So don't confuse that this is different. I mean, that's, I would say, one of the more common errors that I would see on exams or homeworks, is that this leads to some calculation that doesn't have the same static equivalent value. And then I guess the last error that I see relatively frequently is, in this example where, okay, so I'm going to sum my moments about this corner position that we called A, and here's my shear. So here F1 is the only one of these, because this one and this one go through the shear center. F1 is the only one that remains. And so another common error is to say, okay, I'm going about this point, so counterclockwise positive. So F1 times B plus SX times EY, where this is EY, is equal to 0. Okay, so this is very similar but incorrect to the equation that we need to apply. Rather, this is equal to this. This is equal to this. Remember, I drew this big equal sign. So instead, it has to be F1B is equal to SXEY. And so there's a difference, obviously, in signs between the top line here and the bottom line. So this is another common error that I see on homeworks and exams. They are the static equivalent. All right. Okay, so that's it for shear center. Shear center, I think, is one of the cooler concepts that we deal with in structural mechanics. It's just it's in some ways so counterintuitive, but really cool. So I think it's kind of fun. I hope you guys get an appreciation for it as well, or have an appreciation for it by the time this class is over. Okay, so Garrett's asking a question. If the point chosen is your assumed shear center location, but is not the actual shear center location, can you still do the moment about that point is equal to 0? Yes, you can, right? Because you get to choose what point you're taking your moments about. Okay, so let me do this. So, you know, I don't have to use that same cross-section. This could be a reasonable cross-section, right? Probably unlikely, but you never know. And so let's say that I'm going to assume that this is my shear resultant out here. Okay, if I'm assuming this is the shear center, and whatever I do, as long as this assumed shear load goes through the shear center, then its moment contribution has to be equal to 0. And so therefore, whatever resulting forces that I calculate out of this over here, relative to this point, they have to sum to be 0. Now, I guess that would be a third common error that's encountered during exams or homework, is that you're assuming 0 for one load here, but then you assume another position, essentially. You're assuming it's going to be 0 through this point with another part of the calculation. So I only get to choose one point at which to take this to be consistent, to make sure that it's going to be equal to 0. Okay, so now we're going to move on. We're going to address the next topic in our calculation of shear flows. You know, we've actually covered now a couple of shear flow lectures. We're on to our 4th full lecture on shear flow. This is a pretty important topic in structural mechanics. Now what we're doing is we're getting back to a closed cell section now. You know, everything that I've drawn up to this point, at least with regard to calculation of shear flows, was open. Now there's a reason we start with the open sections, and that'll become quite obvious in a minute or two. But, you know, of course, you need to recognize that not all cross sections in any aerospace structure or any structure in general would be open. In fact, probably the vast majority of them are closed cross sections. Now, just a reminder, I don't want you to lose the big picture. These are all beams. Okay, so they go off into the distance like this. And they have a cross section. So we're just kind of talking about different styles of cross section, all carrying these beam loads. In this case, what is shown here is a beam shear force, shear resultant on the cross section as defined by the diagram here. Okay, and you probably remember, if not, I'm just bringing it back up. Well, this is what we derived, was the shear flow equation. And it's a relationship to the bending stresses in a beam. So it is a beam. The shear flow derives directly from the bending stresses, at least in this context. The computed, the shear flows due to bending are due to this equation here. That is, the change in shear flow with respect to the S coordinate system is equal to minus the thickness times the derivative of the bending ZZ stress with respect to the Z axis. And then we then further took that one more step, and after integrating, we found that this was the more complete equation. So this was the differential equation, and this was the equation for Q. So despite that this is a closed section, really there was no difference because this is just describing beam bending relationship to shear flow. It doesn't matter if it's closed or open, this calculation is still the same. So these bullet points that you're seeing now are just the statements that I've made verbally. These are bending equations. They were derived using open thin-walled segment. However, the only restriction was that the walls were thin and it is a bending load in a beam. So the equations are equally valid for open and closed sections, and we're going to now focus on closed sections. Really, the reason we started with open sections was because in an open section, it's really easy to identify a point where the shear is 0, and therefore we can choose a nice convenient S-coordinate system defined from that point with now a boundary condition of Q is equal to 0. So that is a convenient thing that we did and why we started with open sections. However, it's not as easy to do that in a closed section. It's not necessarily intuitive to say, all right, well, here's where I know the shear flow will be 0. So it begs the question, where do we start? And, oh, by the way, if we choose a point, do we know what the value of the shear flow is at that point? And the answer is, well, not always. But we can calculate it. Okay, so let's go ahead and get started. We're now going to take this rectangular thin-walled cross-section. Now, you know, we could get back to Garrett's question, where's the shear center? Well, that's an easy question, right? Because we know this is symmetric here. We know this is symmetric here. You know, there is a degree of symmetry here, like an anti-symmetry actually at that point, and an anti-symmetry. Oh, I didn't draw that last line very well, but you get the general gist. We know that the shear center will be in the center for this thing. But that's not what was asked in the question, so we got to address the question at hand. We, of course, need to also define a coordinate system. Turns out that the shear center and the centroid for this cross-section are both here in the middle of the cross-section due to the symmetries that are existing. So I'll just go ahead and place an origin of a coordinate system there. We're going to call that x and y. But nevertheless, I still need to define coordinate systems for calculating shear flow. And of course, that is an S-based tangent normal coordinate system. And like I did before, I'm actually going to break this up into 4 different segments, multiple segments, 4 different segments. The reason I'm choosing 4 in this example is because, well, so the thickness is constant everywhere, but the magnitudes of x and y are at least piecewise constant in these 4 different segments. So if I break up my sum, an integral is a sum, if I break up my sum into 4 individual sums and then sum them all together, I've still done the same thing. So I'm just doing that this time. I'm breaking my integral up into 4 sums. I'm defining 4 coordinate systems. I'll call them S1, S2, S3, and S4, as shown in the diagram, with the directions associated with the arrows that you see. So in this case, the directions are positive clockwise around my cross-section. Now, of course, you know, looking back at the calculation that we're doing here, it's this calculation. So what do we know about this cross-section? Well, we know because it is symmetric about the x or y, in fact, both axes here, I can set I, x, y values equal to 0. I'm going to assume for this calculation, you know, what was given to you was a shear resultant in one direction. So because there is Sx being equal to 0, I can also cross out the Sx components. And what is left is now, you know, this whole top equation goes away. This bottom equation does not go away, but we can now cancel additionally the Iy values. We get this minus Sy over Ix times the integral. Oh, here I got to cross these out too, times the integral of yt of s ds. And so I've just identified those 2 things here. and therefore simplified my calculation. Now, again, I defined 4 different shear flow sections, subsections really of the cross section. I have section 1. In section 1, again, when you're doing the homework, do as I'm doing here. Make yourself a nice clean table that's very easy for yourself and, of course, for the grader, likely me, to actually quickly ascertain that what you've done is reasonable and correct. So you're going to consolidate these all into a nice little table. So the thickness in each section will be a constant T. The value of Y as a function of the position S1 now is going to be a function of S1. If I go back to the diagram, here is S1. Our Y position starts at minus h over 2, ends at h over 2, and obviously is going to be linear as we transition along S1. So that's just slope-intercept form. We can calculate the slope and intercept really quite easily. And so I've done that here. Y is equal to S1 minus h over 2. We can double check S1 equals 0 minus h over 2. S1 equals h. We get plus h over 2. So that is a simple calculation. Now here's where it gets a little bit trickier. The magnitude of the initial Q1, this is Q at S1 equals 0. This is the boundary condition. We don't know what it is. So I'm just going to say it is going to be equal in magnitude to Q0. We don't know it's 0, so we cannot assume it's 0. Okay, section 2, I can go through these quickly. You've seen it a bunch. Thickness is constant. For this cross section, the Y value for the entire duration of S2 is going to be equal to h over 2. And the magnitude of the initial constant, the boundary condition at the origin of the coordinate system, we don't know what it is, but we do know that there's this shear flow continuity, meaning that the value of Q1, that is the Q that is calculated from this stuff, evaluated at the position H, is going to be the boundary. So as we calculate Q starting here and moving up to here, it has a value here. That is the starting value for the next segment. Okay, section 3, similarly, we still have a constant T for these lecture examples. That's going to be true. In the homework, it might not be. In general, for real structures, it might not be. Y of S3, so this is the Y value. Again, this is a slope-intercept form. It's linear from top to bottom. At S3 equals 0, it has to be positive h over 2, and it decreases as you go forward, so this checks out. And then last but not least, of course, the magnitude of the boundary condition is simply the evaluation of the calculation of Q in the second section as we move off to the right. It has a value here. That is the starting value for the next segment. And then last but not least, of course, the last one is a constant cross-section T, constant thickness, I should say, the value of a Y being at the bottom. We're talking now about this segment here. It's always going to be at minus h over 2 in the Y direction. And of course, the value of the boundary condition, same arguments as before, it's the value of the Q calculated from this stuff now gets put into here where the S value of S3 would be equal to H. All right, I'll make sure that you guys have a little bit of time to copy these values. Not too much to copy, so I won't wait for too long. Any questions while I'm pausing for just a second? Nicole asks, can you explain the Y of S3 and Y of S1 again? Sure. So Y of S3 and Y of S1. So these are values of Y. So of course our coordinate system is at the origin here. So we're trying to relate the S positions to the value of Y. So here at S1 equals 0, the origin of the S coordinate system, it has a value of y that works out to be, minus h over 2. Because here's h, right? I don't know if I kind of have blocked it over there, but there the whole thing is h high and b wide. And because of that, this point is minus h over 2. This point is plus h over 2. It's linear in between them, and so that was just slope-intercept form. Same thing on the opposite side, except now the origin is at the top plus h over 2, and it ends at the bottom minus h over 2, again slope-intercept form. We can calculate the relationship there. Okay, so the next step, of course, is to integrate the equations. I'll go back here to the equation we're integrating. The simplified version of this equation is now q is equal to minus sy over ixx times the integral from 0 to s y t ds. So we're integrating this equation. We know sy, we know ix, we know y, we just wrote them down, we know t, and we, of course, integrate over ds from the origin to the end of each of these. Don't forget, of course, the integration constant. So there was a plus q initial, q of s equals 0 that we're tracking. Okay, so all of this is the equation we're integrating. So if I go through and do that integral, here's what I get. It's pretty straightforward, actually. Q1, just to remind you, so the value of y was linear in s. So when we integrate with respect to s, we get s1 squared minus hs1. So we get a quadratic equation. Then, of course, we're carrying forward that boundary condition plus q0. We don't know what that is yet. Do that same integral. We plug in the value. So to get the boundary condition here, we're applying s1 equals h into this equation. So h squared minus h squared, you're going to get a 0 there. The other part, q0, comes down again. So this transfers down. And then q2 was constant with regard to y, so you integrate with respect to s and you get just the value s now, so it's linear with respect to s, minus s1t over ix hs over 2 plus 0. So this was this portion here evaluated at s1 equals h is what comes down there. Same thing with section 3. Of course, now we're going to get a little bit more complicated because in section 3 we need to know the value of q2 where s2 equals b. So before I hop to the next slide, we'll just evaluate that now. So that'll be hb over 2. So we're going to get syt over ix, that's hb over 2 plus q0. That's going to be our boundary condition. So boom, that is this part here plus this. And then this portion here is the integral that we previously alluded to. Again, that was linear with respect to s. When we integrate it, it becomes squared. So s3 squared minus s3h. So you get a quadratic equation. And then last but not least, we integrate q4. We still have to now apply the magnitude to get our boundary condition on the right-hand side. We say s3 is equal to h. So h squared minus h squared. This portion goes away. We get this b over 2 come down here. We get the q0 comes down here. And now this portion is the integrated portion, which because it was a constant becomes linear. So hs4 over 2. Okay, so in summary, what do we know? With this resultant shear load, we can calculate shear flows. We don't quite have it all. Each one of these still has an unknown Q0 in it, that's because we didn't know the magnitude of Q0 at the point that we started. Okay, recall that, what's the unit of shear flow? It is force per unit length. We can integrate along these segments and replace it with statically equivalent forces. Again, the arrow directions have to line up. So I'm going to call it F1, 2, 3, and 4. And in each case, I'm integrating Q1 or Q2 or Q3 or Q4 with respect to the ds, local ds. And so having done that, and also keep in mind I'm doing this now because I'm replacing the force per unit length. I'm integrating from one end to the other. I do apply the limits in this integral. So from 0 to h, and then separately from 0 to b, and then separately 0 to h, and then separately 0 to b. And I can go ahead and then calculate these forces. So if you remember, Q1 was second order in S. So complete the integration with respect to S. It becomes third order. Evaluate the limits, and this is what we get. SYT over IX. H cubed over 12 plus HQ0. Still this unknown Q0. We don't know anything about it yet. F2, we can compute that integral as well. That one was linear with respect to S. Ends up being quadratic. And then you apply the limits and you get this B squared present. So SYT over I, B squared H over 4 plus B times Q0. Do it again. I know I'm going kind of fast. I guess I should let that reside on there for a little while. For this lecture example, these are very straightforward integrals to do. In the homework problems, it's going to get a little dicier, actually, on purpose. And while you guys are copying down these answers, I will mention that for many problems, where there's curvature to your cross section. So one of the homework problems looks sort of like this. So at every given point, there is a different direction of what I'll call df, which is equal essentially to q. So because the direction is different at each point, now when you sum the moments and sum the forces, you have to be very careful about how you are calculating the components of force in the x and y direction, and of course the overall moment associated with that differential force. So that's a little hint about what's to come in the homework problems. But for these problems where we have constant directions, at least for the subsections of the integral, we can actually resolve individual forces rather than differential moments or differential forces. Okay, sections 3 and 4 are going to be quite similar to the other ones. So again, if you remember, Q3 was quadratic. When you integrate quadratic, you get cubic. So this is going to be a cubic equation. We end up, and then you apply the limits, and you get this h cubed over 12 minus bh squared over 2 after applying the limits, and then you still get this Q0 hanging out here on the right. Last but not least, F4. S was linear in Q in this segment, becomes second order when we integrate it, so b squared h over 4. And lastly, of course, we have this thing hanging out Q0 we still don't know. Okay, so and of course the next thing to recognize is that equilibrium has to apply. Okay, we're calculating the shear flows due to a resultant shear force. Of course, in the assumptions that we did here, that shear force was in the y direction. There was no x component. So the overall sum of all forces in the x direction has to be equal to 0 for this problem. And then, of course, you recognized, let me draw on the chalkboard here. So here was my square. I said this was F1 in this direction. This was F2, which is in the positive x direction. Then this one was down because we're following the convention of the arrows. So F2 plus F4, those are in the opposite direction. So it's F2 minus F4. And oh, by the way, if we compare this one to this one, flipping back and forth a few times, you see that they are identical. So lo and behold, since they are identical, this equation, it confirms that we haven't made a mistake yet, or at least makes us more strongly suspect we haven't made a mistake, but it doesn't really add to our understanding of the problem in any way. Okay, so that is one equilibrium equation. We have a couple more. We can sum the forces in the y direction. Okay, keep in mind that we have this was F1 over here was positive upwards in the y direction. F3 was downwards. So this plus this is actually, you're going to get this minus this. F1 minus F3. And those are statically equivalent to Sy. Okay, this is again that circumstance. You're not summing F1 minus F3 plus Sy. It's rather F1 minus F3 equals Sy, since they are statically equivalent. Now, unfortunately, this one also doesn't help us that much. And the question, of course, is, well, why not? Well, if we look at these magnitudes, that's F3, that's F1. When we plug and chug, by the way, and both of these, F1 and F3, have Sy in them. So when we plug and chug, this equation just simply becomes Sy is equal to Sy. And that doesn't help us terribly much. Q0, by the way, gets canceled in that calculation. So once again, we're confronted with the idea, well, we probably haven't made a mistake yet, but we still have no clue what Q0 is. So we don't know what the shear flows are yet. And so last but not least, we have one more equilibrium equation that needs to be applied. Anybody remember what it is? Yeah, it's moment. Thanks, Scott. So in order to actually determine what Q0 is, we need to do a moment equilibrium calculation. Now, once again, with any moment calculation, you want to sum it about a convenient location. In this problem, I would say there are, potentially a number of convenient locations. One of them is we already know where the shear center is. And so, in this case, I might take the moments about the shear center. It's actually at the origin of our coordinate system, and it's actually at the centroid. So there's three reasons why we might choose to do it at this one location. So the summing of the moments about the shear center gives us, and remember this is 1, 2, 3, and 4. So if we define, in this case, just for convenience, I'll define my moments as positive clockwise, and then all of them end up being positive. So you get F1 plus F3. So that's this one and this one. They are both a distance b over 2. This distance, total distance is b, so b over 2 is their moment arm. So F1 plus F3 times b over 2 plus F3 plus F4, F2 plus F4 times h over 2. So their moment arm there is h over 2. The sum of all of those, since the actual shear was through this shear center, that has to be equal to 0. Now this ends up being a plug and chug exercise again. And when we do that exercise, we end up being able to calculate the value of Q0 from it. And the magnitude of Q0 is SYT over IXX BH over 4. And remember, so this is the magnitude of the shear flow here at this corner where we started our first coordinate system. All right, Nicole's asking a question. Yeah, so Nicole says, so the sum of the force in the y direction is not Sy plus F3 minus F plus S, sorry, I'm having a little trouble speaking. Sy plus F1 minus F3. It is not that, correct, because the Fs and the shear forces are the same. So you can't add them together because they are the same. Yeah. Yep, absolutely. Okay, so now we know Q0. Once we know Q0, we can go back and plug that in way up there, and we can know all the shear flows in each individual segment and generally be happy-go-lucky. Okay, so in general, so the way, so you know, this, the way I've taught it to you now, the last, I don't know, what is that, a half dozen or more slides, is the way I like to think about that problem. Meaning that I don't convert it to some other type of problem when I do my own calculation. In C.T. Sun's textbook, however, he actually makes a different suggestion. He suggests that you sort of think about it as an open tube with an initiation point with a non-zero Q, which is functionally the same thing. Okay, his language on it is just a little bit weird to me, and I don't think in those terms. But if you like the way that that is described in his textbook, I've got absolutely no problem with it. It is perfectly legitimate. One of the reasons why that can be challenging, though, is of course, if you're making this little jump to having an open, you're treating it as an open tube. Now your shear center location is going to be more difficult to calculate because it's open. You're not taking advantage of the symmetry anymore, and so you kind of have to drive this integral to 0 in order to do so, meaning that there would be no twist in the resultant section. And so that's, you know, it's something reasonable you can do. I just happen to like the way I've presented it myself a little bit better. Both perfectly legitimate, equally usable, valid. One works better with my mind. Whichever one works better for your mind is the one you should use. Okay, this is more on what he's doing in his stuff. So Q0 is this constant offset over the integration domain, and it gets a little, I think it's another thing to memorize. In my view, it's just apply equilibrium, track your work carefully. You do it fine. Otherwise, for his, you kind of have to remember this form of the equation, which is fine. Again, it works great. It really does work fine. It's just another thing to remember. So that's what the textbook suggests you should do. Okay, are there any questions out there on this? I suppose I should watch the time. What time is it? It's 3:34. We have about 15 minutes or so left. Okay, I'm not hearing any more questions come through on this, so we'll go ahead and jump to the next lecture. So now we're going to talk about what is referred to as cell torque, torques of cells within a aerospace cross-section is what we're thinking about. Really, it doesn't have to be aerospace. This could be any section. These are thin-walled torsion-carrying members. Okay. Now, what we have just finished talking about, and in fact, it took us, essentially the better part of 3.5 lectures to cover, was this idea of shear flow. First of all, conceptually, what is it? And then secondly, how do we compute shear flows? And then resulting forces, moments, equilibriums that come from the shear flows. For ultimately, those were all bending calculations. Those were beams that were carrying loads. And of course, anytime you're carrying loads in a beam, typically you're going to be carrying a shear resultant because of the beam equations. The moments and the shears are related through a derivative. So if you're carrying a moment and that's changing, you have a shear. So consequently, those were shear flows, shear stresses in the cross-section resulting from bending loads. Now we're going to do shear flows, but instead of coming from bending loads, we're actually going to treat them as coming from torsion loads. So, big picture, what we're doing is we're treating these things using, much like we separated the axial load from the bending load from the torsion loads previously, and then if they all apply at one time, we use superposition to bring them together. We're doing the exact same thing now for shear flow. We know how to do shear flow for bending calculations. That's been the last 3 lectures. Now we're doing shear flow for torsion calculations. Okay, we're going to start in this case actually with torque for a closed cell. We'll get to open cells later. Open cells are harder in this case. Closed cells are easier, so we'll start there. So what do I have? I have a I have a cross-section. I shouldn't say a constant cross-section because it could vary as a function of the z-axis. But I've got a cross-section of a thin-walled torque-carrying member, sometimes called a torsion shaft, or like a crankshaft or something like that. And it has an applied torque at each end. Now, like we assumed or observed in the bending calculations for shear flow, we're going to assume that this wall, the wall thickness of this thing, is relatively thin. Now, when we talk about thick or thin, those are relative terms. We need to have a reference. So in this case, our reference is thin relative to some minimum cross-section radius. So this doesn't have to be a circle. We're going to identify the center of twist. We've talked about that in the past. And then the distance to the maximum, furthest away from the center of twist, we're going to call that our min. Actually, I should say, so that's our max. And then the closest point is our min. And so in this case, the wall thickness, in order for these calculations to be reasonable, needs to be small compared to our min. Guidance on that, maybe, I'm going to say at least the radius needs to be 5 times larger approximately, maybe a little bit more. The larger that ratio, the more accurate these calculations become. Again, we have a tangent normal coordinate system, so S is in the direction of the tangency, so it follows the midline of the thin-walled section. Of course, the normal is perpendicular to that. And like we've described for beam bending, we said that the thickness now, the reason all of this is convenient is because now we're describing the thickness as a function of S. So where are we within the cross-section in the S coordinate system rather than with regard to X and Y. So the thickness is now a property of the cross-section, and your position within it could generally be a function of S. So, we've kind of begun to lay out some of the assumptions that we need. So, the thin-walled assumption is big one. Another assumption is that the the overall torque, this is the torque, by the way, that is this magnitude here, the applied resultant torque for this torque load-carrying member, causes only shear stress at the wall. So this is a pure torsion problem. We are not evaluating bending with these calculations. We know how to do bending. In fact, we just finished it. But in the end, if we've got a bending problem that has a torsion overlay or a torsion problem that has a bending overlay, we'll use superposition. We'll solve them separately and then superpose them. And so in this case, for these calculations, we're assuming that we're only dealing with the torsion portion of this. And much like we did with the bending aspect of the problem, we're going to say that there is very little room for variation in the shear stress through the thickness. And so we're going to assume that it is a constant shear thickness or shear stress through the wall thickness. And we'll use the average. And why do we assume the thin wall? Again, so if I make this assumption that this distance from wherever the center of twist is to the wall inside versus outside, if you guys remember, the shear stress was proportional to the distance from the axis. And so what we're seeing here is that because this is small, the variation across the thickness is relatively small, and we can just use an average representation and not have a lot of error creep in. Now, this is in some sense a repeat of what you'd seen before. So we had deduced equilibrium for shear flow calculations. You've seen this before. This was at the beginning of the bending calculation portion. And what we saw was, and this is a equilibrium element. We have bending stresses, sigma zz on each side. There is a change of sigma zz across the distance dz. So this delta sigma, I'm having trouble with my mouse today. It must be just in a bad spot on my desk. It's not drawing well. All right, there, that's a little better. Okay, so sigma, this is the change over this distance delta z. We're going to get a small change in bending stress, as at least theoretically, although in a minute we're going to make an observation about that. And then, of course, we have the shear flow. So this was the calculation that we looked at previously, and it ultimately ended up being this. And in the limit, as these lengths become small, this became a derivative, and this is that derivative. So dq ds is equal to minus t d sigma z dz. This is what we derived at the beginning of the first shear flow calculation lecture, and it's related to the bending stresses. The shear flows are related to the bending stresses. Now, importantly, we're stating that our calculation is a torsion calculation. There is no bending. So what does that mean? That means that sigma zz ultimately is going to be equal to, well, we can treat it as constant, or we could treat it as zero, essentially. No bending. There is no bending stress. So if the right-hand side of this equation becomes zero, what we end up is we end up with a shear flow that's now going to be equal to constant values. So integrate dq ds, we get q is equal to a constant. Okay, so if I go back to this equation, I then basically I can knock out the bending stress because that's equal to zero. I define the shears as being constant. We're a little bit careful about tracking our forces in equilibrium. So, in this direction now, I'm looking at this shear flow and this shear flow with a constant shear stress. What we see here is the sum of the forces has to be equal to zero, which we can then say is going to be equal to, well, we know the shear flow here, we know the thickness here, we know the length delta z there, So we know the differential force in that direction. We know the differential force in that direction. We know they sum to be equal to 0. And so what we see is the following. So shear stress on one side times the thickness, because that's the definition of shear flow, shear stress times thickness, times that length is equal to shear stress times thickness. So shear flow times length is equal to shear flow times length. Shear stress times thickness times length is equal to shear stress times thickness times length. So what we find is that there's this relationship between the shear stresses and the thicknesses. We're not saying the shear stress is constant. We're saying the shear flow is constant. So as the thickness changes, so does the shear stress. All right, I want to make sure I'm not moving too fast. You guys, can you give me a thumbs up that I'm not moving too fast, that you guys are ready to move forward? Okay, I'm seeing at least one student who wants just a little bit more time. Unfortunately, I can only see about 5 students at any one time. Okay, can I get a thumbs up again if you're ready to move on? Okay, I'm not seeing any objection. If anybody objects, chime in with your mic because you're off screen for the moment. Okay, so, and we really just have a few minutes left here. So in summary, what we find is that the shear flow, and again, we're calling that Q, it's constant along the wall of a cross section of a monocoque beam under pure torsion. So this is a thin-walled beam under pure torsion. You're going to have a constant shear flow. And again, in your mind, what does that mean? That means shear flow times, shear stress times thickness. That's what's constant. So if thickness changes, shear stress changes. If shear stress changes, thickness changes, and so forth. So all of that brings us to this point. This is just sort of a repeat of what I had on the last slide. Again, sort of showing the same general approach that I had referenced back to the prior slide, but this one's a little bit better because it doesn't, this one doesn't have the beam stress confusion on it like the last one did. Now, we got to be careful. So this is, again, this is about pure torsion, right? If bending was present, we can't say shear stress, we can't say shear flow is constant if there's bending, because now it's a function of the changing shear bending stress. But if we set up and separate bending from torsion, which we know that we can do, and then we only deal with the torsion portions of it, we can then later bring back that other aspect of shear flow through superposition. These are really the same equations. Now, I think we have 1 minute left. The next calculation is, I think, just a little bit hairy. It's not too bad, but it's hairy enough that if we start it, I think we're going to need to spend a good 5 to 10 minutes on it before you guys would feel comfortable moving on. So I think I'm going to instead pause here. We'll conclude the lecture. I'm happy to take your questions. I'll hang around for a few minutes. If you don't have any questions, then have a good evening, and I'll see you next Thursday, or I should say on Thursday, 2 days from now.
I have a question if you have a minute.
Sure.
So I'm still a little confused about the closed wall thing with the y of S1 and y of S3. I know what you mean by the y of S1 equals 0 equals minus h over 2, but I didn't know what you mean by it being like linear.
Okay. So let me start with a really simple concept, okay? We'll start simple and build from there. So here, if I have an XY coordinate system, okay, I can, I'm defining a coordinate system, a new coordinate system. Let's say I define my new coordinate system S here. So the origin of S is also at Y, at the origin of Y. As Y increases, so does S. And in fact, it increases linearly with Y. We're relating these two coordinate systems. Now, if I wanted to call the origin here S0, and I were to call another point S1, so this is some distance all the way up here. Okay, so S0 and S1 are two extremes of this coordinate system. Now, if I define this in terms of Y instead, if I wasn't concerned about S, I could have called this distance, we'll say, why not? Let's say that this is 5 total H's. So 5, I shouldn't use 5 because that's too easy to confuse with S. We'll call it 4H. So 4H is the distance from this point to this point. And in the S coordinate system, it's S1 minus S0. So 4H is equal to S1 minus S0. All I'm saying when I say it's linear is that the relationship between the S coordinate system and the Y coordinate system is linear in either S or Y, and you can actually compute what it is because you have a slope and intercept form here. So if this is Y is equal to 0 here, and Y is equal to 4H here, and S is equal to 0 here, and it's equal to, some distance S1 minus S0, call it S1 if you want. So 4H is equal to S. It's linear. It's just a linear relationship. Now, by contrast to that, what's the difference? So if we had, let's imagine now a circular cross section. Okay, I can define X and Y. I can also say, all right, well, I'm going to do a tangent normal where I'm going to have S start here. Okay, for sake of discussion, we're going to say that this thing has a total radius R. So Y at S0 is equal to R. Y at S, well, we're going to call it S1, is equal to 0. This one is not linear, though. Why is it not linear? Well, we know that the Y relationship is now based on this angle theta that is this, an angle defined here. Right? And the total distance, the arc length from here to here is going to be R times, what is that, pi over 2? Pi over 2 times R. So the total length is, this arc length is pi over 2 times R, but that is a longer distance than R. And oh, by the way, the relationship is not linear. So that goes as, what is it? Cosine, it ends up being cosine of theta. If I define theta as this angle here, so the non-linearity is that you have to multiply by cosine of theta and do a transformation of coordinates from R theta to S to X and Y. You need to be able to move back and forth between those three. Do you get what I mean by nonlinear now, Nicole?
So if it's not like how the boxes or whatever were like straight lines, then those ones were linear, but since this is curved or something?
Yeah, I mean,
Or,
that's functionally true for this scenario. So if you had an XY coordinate system and then you had a thin wall that went off like this, and you defined an S coordinate system here, because the slope of this is constant, then the relationship between Y and S is linear. But if this was curved, like you said, then the relationship is no longer linear. So yeah, you're correct.
so then if you had to write something for like the y of S1 or whatever for the circle, can you explain how you would do that again?
Well, sure. Let me give you a really simple example. Okay. Now you're going to have to do this for homework, and those aren't going to be quite as simple as the one that I'm going to do now. But let's say that this is an X and Y coordinate system. So I want to have an S coordinate system as well, but I'm going to start it here because it's just easy. And then also I can overlay, because there's no reason not to. I'm going to use an intermediate coordinate system, which is going to have theta in it. So we're going to have an R theta coordinate system. So we have X, Y, R theta, and S. Now in this case, we need to relate the arc length, which is the S coordinate system position, to R and theta, so it'll be real easy to start there. So R times sine of theta is equal to Y. R times cosine of theta is equal to X. And then you also need to recognize that R and theta are related to S as well, but that's a slightly different. So S is equal to R times theta because it's an arc length, right? As you sweep from here up, the arc length is R theta, but the position X and Y is related to R sine theta and cosine theta. So you need to go through and do a transformation of coordinate systems. And I don't know if you recall at the beginning of the semester, one of the things that I emphasized was to go back and sort of reteach yourself calculus if you had forgotten it. And one of the things that you need to do very well in structural mechanics and fluid mechanics and all these higher level mechanics courses is do coordinate system changes, coordinate system transformations. And so this is a clear example of you have three different coordinate systems. They all have to do the same thing, but it's a heck of a lot easier to calculate these in an R theta system than it is in an XY system.
So what are you trying to get it in terms of, like, which coordinate system are you trying to get it to?
Well, for the purposes of the shear flow, you want it in S. But, well, so let me go back to the equations, make sure I'm on the right presentation here. So it's this equation here that gets a little quirky, we'll say. So here, this equation, the shear flow, it's written in terms of both S and X. So arguably, often the easiest thing to do is to so for a problem like I was just describing, this circle, the S coordinate system and the X coordinate system, you just saw the relationship. X is equal to R times theta, sine of theta. Y is equal to R cosine of theta, and S is equal to R times theta. And so you need to do all these transformations, and in the end, to do the shear flow calculation, the easiest one for this particular problem is to actually convert the X and the S both into an R theta system, and do the calculation. Now becomes Q of R and theta. And then after you've done the integral, then you have to go back and put it back in terms of S probably, or you may need to potentially. So back and forth between coordinate systems, real critical.
Okay, so you would like maybe integrate in the R theta and then go back to the S?
You might have to go back to the, you might have to, you might not. In fact, there are many circumstances where you don't have to. But that sort of depends on what's being asked in the question. For example, if I ask you to calculate, well, what's the shear flow at this location right here? Well, if you can calculate that shear flow in R theta, then you just say, okay, well, theta is equal to, 45 degrees. And so I can express my answer easily if I have Q solved in terms of theta. So then, I get to my answer. But if instead, I'm asking you something else, like, oops, the the homework problem that you have at hand, one that I just assigned a couple of days ago was this one. I think I assigned this one. So it's kind of like hemispherical top and bottom, but it's straight on the edge. So now it's not as, you can't express this portion over here in terms of R and theta anymore. It's non-intuitive. It doesn't make a lot of sense. So once you get from one side to the other, then you need to go back and switch to a linear coordinate system on that side.
Okay, that helps. Thank you.